Well, it's usually habitual to sort of thank the organisers here, but it's one of these slightly embarrassing things that I had to confess to my vanity, having put myself on to talk. It was only a little bit of a shock that I realised I'd done that sort of at the end of last week. Are you sure? Well, okay, then I asked you to speak. I see. Okay. Well, I think anyway, but vanity is something to own. Anyway, so today I want to talk about celestial symmetries from Twistor space, but I'm conscious of a kind of rather diverse audience, and so it's more important that you ask questions and get me to explain things properly than for me to get to the end of my slides. And I do promise to try and stop by 3:30 or whatever the limit is. So this is joint work with Adam Kumech, graduate students, Romain Rusiconi and Akshay Yadishpur Shrikant, and but it does feed off work by Friedel Prancetti and Ricariu, or it's really trying to understand their work, which would then in turn fed off work by the whole Harvard group, Andy Strominger and Alfredo, who'll be talking later on this week, and plenty of friends there. Some of the technology uses older work with Tim and Atul, and it also sort of feeds back on older work still with Matchik from the noughties, and also work with some sort of local heroes, Simon and Roland and David and so on. So okay, so where do we start? Well, I guess we can go back a little bit in history to the 1970s, before I started with Ted Newman. And just to give a little bit of background here, he was perhaps one of the worst, sorry, that was a complete, the first holographers, and I would say a good one, I mean, not worst at all, in the sense that he had this image that you could, there are all these discussions in quantum gravity about no local observables and stuff, but if you have an asymptotically flat space-time, you can try and sort of look back into the bulk of space-time to reconstruct even the space-time events, and the way to do that was to start off with a space-time event. You follow its light cone out to null infinity. So I'm assuming everyone here is happy with null infinity. Null infinity is, well, I'm drawing it as a cone. It's really S2 cross R. This U is the up and down R factor. And the light cone, there's a celestial sphere. So it's intersects scry and a picture a bit like this, where that circle is really a sphere. And he had the image that, sorry, I should have somehow turned off my notifications. He had the image that you could characterize how it is that a light cone would intersect null infinity. And in fact, he introduced what was called a good cut equation. And some of this was partly associated with his terrible sense of humor. This is where the good Cohens would go out to infinity, out to heaven. Sorry. So anyway, so he introduced this space of good cuts, and he discovered that with this condition, which is an asymptotic shear free condition, you would only get a 4-parameter family of cuts, but he failed in his initial task. He did not find the original space-time as this 4-parameter family of cuts. Instead, he found a self-dual space-time. So the Weil tensor is self-dual, and hopefully you've heard a lot about such things. Furthermore, it's Ricci flat. So it was pretty good, but sort of no cigar, so to speak. But what it does is it reconstructs the self-dual space-time that has the same self-dual data at null infinity as the original space-time you first thought of. It has the same, the asymptotic shear is the data. It has the same asymptotic shear on one side, but 0 on the other. Roger Penrose, this formed the seeds of Roger's nonlinear graviton construction. And this was how it was that Roger Penrose actually developed his twistor theory by introducing a twistor space at null infinity and then sort of abstracting it. Eventually, he realized he could throw away null infinity and get a much more general construction, which just used a deformed twistor space. And this nonlinear graviton construction has formed a paradigm for much of twistor theory in the subsequent sort of development of the subject. But yeah, so it's a big improvement because it applies beyond the asymptotically flat sector, beyond the, you can have cosmological constants and all that sort of thing. And the other thing it did is it really embodied the complete integrability of the self-dual sector. I mean, already Ted Newman's construction was doing that because it was basically specifying free data at null infinity and then solving an auxiliary two-dimensional problem for these so-called good cuts. You were writing down the full four-dimensional solution of a four-dimensional differential equation. So in that sense, it embodies the complete integrability of the self-dual sector. And one of the things that Matchik and I did sort of some 20-something years ago was to show how, for example, it led to a hierarchy of hidden symmetries and things like that. And really what I'm talking about today is how these symmetries have been rediscovered in a completely different context in the celestial holography program, and how some sort of complicated work that was done by this kind of group here, this Friedel, Presenti, Reclaro, to try and understand that in space-time terms, can be understood by doing some Noether arguments within twistor space, and I'll be going through some of those later. And but to start off with, then, before I get into all of the twistor theory and how these hidden symmetries come about and how you understand these things, I want to just give a sort of brief summary of the celestial holography program. It's not really needed for the kind of rest of the talk, but I think it just will add some color or something. Anyway, there is a celestial holography day later on this week, and maybe it gives some introduction to the sort of things people are trying to do. So this is celestial holography on one slide. So what's the idea of celestial holography? You want to reformulate, I mean, it's very much this Newman type idea. You want to reformulate Einstein's theory of gravity in terms of some theory, some ideas that are going on the boundary of space-time at null infinity. And holography really originates in quantum field theory. Modern holography originates in ADS CFT, modern field theory. And one of the sort of ways that you express this is by saying there's some scattering amplitudes in the bulk. So they are asymptotic quantities. They can be understood in terms of correlation functions of some field theory on the boundary. But because the boundary is conformal, it actually has to be a CFT. So that's the usual ADS CFT. The infinity of an anti-de Sitter space is a conformal boundary. So the theory that you'd want on the boundary would be a conformal field theory. And so what I'm writing on the left of this equation is meant to be the scattering amplitude for scattering of, I was just gonna, is there some chalk somewhere? Ah, okay. So I mean, I just want to do a very crude sort of in and out sort of thing. You've got some particles coming in from minus infinity and going out to plus infinity. And because they're gravitons, they have K1, K2, K3, and so on, and going on up to Kn. So these Ks are in that formula, they're meant to be null momenta, and then when they hit null infinity, the operator is going to, in some sense, depend on the momenta of the particles of the fields that are interacting in the bulk. So you imagine the gravitons interacts with the null can come out at infinity again. So to really make it more like a CFT, you'll notice that null infinity isn't really a conformal manifold in the normal sense, because we're working with asymptotically flat spaces. If you're on ADS, it would be an honest conformal space. You could think of it as conformal Minkowski space, 2 + 1 Minkowski space if you're on anti-de Sitter space, or just S3 if you're working Euclidean. But here, what the celestial holographers do is they take this null momentum and they express it in terms of the energy, omega I, and a Riemann sphere coordinate, Zi. So you just write it out in a similar sort of way to the way that Ted might have done sort of 50 years ago. And then the idea is that this putative operator that you're trying to learn about, you can expand it in the energies. And so then this HP is going to just depend on the Riemann sphere. And then you really can think about sort of a conformal field theory on the Riemann sphere. Okay, so we, as it happens, we do know rather a lot about these scattering amplitudes for gravity now, certainly at tree level, with some beautiful formulae that David introduced with Freddie Cajazzo 10 years ago, and 12, sorry, and so on and so on. We know a lot about these amplitudes now. So the celestial holographer has been trying to sort of say, well, what is this theory here, these OKs? And okay, so the first thing you do when you have a conformal field theory is you ask about these so-called operator product expansion of the operators. So what you do is you want to, these H's just depend on a point on the Riemann sphere. What happens when those Z's get close to each other? And so when the Z's get close to each other, these null momenta are pointing in the same direction. So it's well known in the amplitude story that such that these amplitudes develop a singularity when two of these momenta become parallel, because roughly speaking, you've got K1, K2. When they become parallel, their sum is a null vector, and there's a propagator linking it to the rest of the diagram, which has a singularity, and that has a universal character. And so this group in Cambridge were able to compute the operator product expansions of these HPs, and then Andy discovered that the algebra that they got was something sort of well known, and it has this rather fancy name, LW1 plus infinity, which is a way of, I think, sort of trying to sort of impress people that it's something very impressive. But this is just Hamiltonians on the plane. I'm saying C2, but they're holomorphic Hamiltonians on the plane for area preserving diffeomorphisms. But you've also got a loop variable as well. And you can do a mode expansion of these. You do polynomials on the plane, and but sort of the loop variable can be both positive and negative, and you get this sort of algebra coming out, and I'll explain how that happens a little bit later. So this was sort of, wow, we can actually do something. We can calculate OPEs, and look, we get this famous algebra. How did that happen? Where's it coming from? So now this is all a bit abstract, and so the Friedel-Franceschetti recount. Yes. Well, it certainly does that, yes. Well, I think you can get the Virasoro group, but I mean, I think you'd need to quantize. You didn't need to do a. Sorry, did I say something wrong? Sorry, there's no Virasoro. Oh, sorry, it's the other one that contains it's a lambda deformed that contains. Yeah, sorry. I was getting muddled. Yeah, no, but there's no SUN, for example. I mean, it's the same thing. It's the same thing as what we were talking about sort of how many years back. Okay, so how do we understand these in a bit more space-time term? And so what Friedel, Prancesi, and Rotario did, and this was sort of improved by some other authors, was that they said, well, can we understand this in terms of the asymptotic gravitational phase space? And so here I have to just do a little bit of a crash course on what the gravitational phase space looks like at null infinity. So null infinity is, as I was saying, it's just R cross sort of S2. And we're thinking of S2 as really being the Riemann sphere with stereographic coordinates Z and Z bar, and U then as being the R factor, the Bondi retarded time. So you just think of that as R minus T on space-time. And so the radiation data of the gravitational field is encoded in this so-called asymptotic shear. It's the shear of the outward going light cones as you meet the outward going U equals constant hypersurface as it meets Scry. What's the last gasp of that? And so you have these this complex function shear, this function of U, Z, and Z bar. And this is, for example, related to the Weil tensor components at Scry. The Weil tensor vanishes, but you know the one over R components or something, the leading parts, can be reconstructed from these psi's. But if you want to go lower order, then you have to solve these asymptotic Bianchi entities. And so as I say, you've got psi 04, psi 03 just locally given, but then psi 02 and psi 01 and so on have to be obtained by solving these equations. But this is a U equation, so they're determined up to boundary terms. But in fact, it's well known that if you want to write down things like the Bondi mass formula, which is the most elementary charge, this is what gives rise to what are known as the super translations, where U just gets translated by some spherical harmonic L equals 0 or 1 spherical harmonic in Z and Z bar. We'll need psi 2, so you have to solve these equations to get there. And FPR observed that you could just continue these equations indefinitely. So if you put QS, calligraphic QS is equal to psi 02 minus S, you could write down this infinite sequence of equations here. So this would give you the lower Weil components, but it would carry on. And then they wrote down some complicated integrals for these QS charges, which were meant to somehow, in some sense, correspond to this tau here. So the QS is just sort of bits of curvature or integrated curvature on Scry, but the tau S is then meant to relate to whichever harmonic, whichever mode we've got here. But those Qs are meant to be the generators associated to these H's here. Yeah. Yeah, maybe. Sorry, I'm not sure that I have a good answer for that. Because of course these things, these calligraphic cues, you think of them as Weil tensor components. They have a life as honest objects. Yeah. Yeah, so the psi's end, and in fact, sorry, there's other things they observe here that these, I didn't want to write it all out, but the story goes on. So the psi goes down to psi 0, or psi 0, 0. But then if you just take psi 0 and expand in R, so you've got the psi 0, 0, and then you do a sum over kind of S or something, then these QS's, then there's some R to some number there. So in fact, they're in the tail of the expansion of the psi 0, 0. But the reason I didn't include that is because there's also junk.
Expansion upon approach.
And yes, it is, but there's junk as well that you have to know how to get rid of. And they didn't give a good rule for that. They just said that these terms are certainly there, but there are other terms as well that you might need. So they But if you just wanted to define these things up to constants of integration, you could just do it using this equation here. Well, I mean, actually, what we know with hindsight is it's what you need to continue into the self-dual space-time versus what you would get if you were continuing into a real space-time. No, but it's pretty obvious, I think. Yeah. Anyway, Atul, Tim, and I had already at this point sort of identified these so-called LW1 plus infinity or celestial symmetries in terms of twistors, but this lot here all seems rather mysterious, and so what I want to do in this talk is to explain how it is that Atul and Tim and I identified these symmetries on twistor space, and then explain how it is you arrive at formulae like these, and in some sense, this also ties into work of Costello and Paquette, because they too were working with these same kind of generators in order to do their stuff. Oh yeah, sorry, but yeah. So the question is, how do these Qs correspond to those Hs? And how do you get at these, you'd have thought it was going to be something relatively simple, but you then look at this. These are the sort of formulae from their, so they've solved these equations here iteratively. And then they've somehow, this is what these charges actually look like, So how on earth does this kind of rather elaborate structure come out? And so I should say that this structure here, for the charges generating these celestial symmetries, I mean, in FPR, they had one or two of these, and there's some errors, and those errors were corrected by Mark Geiler, and he got a bit further, but there wasn't really a clear sense of where they were coming from. So my claim is at least we now know where all of this kind of structure is coming from, and coming out of twistor space. Okay, so the plan of the talk then is to explain where those celestial symmetries, this LW1 plus infinity, how they are actually represented in twistor space, and that's going to be quite simple, and how you get a hierarchy. And then I want to see, so why should symmetries of twistor space correspond to gravitons? Well, that's something which you see from the Penrose's nonlinear graviton construction. Then how do you get from symmetries to charges? Well, that's something you have to see from an action. So there is a nice twistor action, and in fact, we only need the twistor action for self-dual Einstein gravity, which is something which has now been known for some time. And so then you've got to get down to the nitty-gritty of actually computing these things, and anyway, so with a bit of time, with a bit of luck, I'll have enough time to at least explain where the sort of Branson-Todd formula comes in, and where some of the complications are coming from. To be honest, their computations weren't sensitive as to whether they're going to a self-dual space or the real space. Because all they were doing was they were looking at the equation, which is really adapted to the self-dual space. And, that's an open problem. Absolutely. I mean, certainly, I mean, these things, they all have a life out of infinity. You can define everything out of infinity. And one of the things that you rely on is that the self-dual sector of gravity, the phase space of self-dual gravity can be identified with a phase space of full gravity at infinity. And so if you're not in the business of evolving into the bulk, the structures can be carried from one space to the other, one phase space to the other. Okay, so I just wanted to say what this W infinity, LW infinity, LW1 plus infinity all were. So first of all, I mean, this is a story that goes back to Zamolodchikov in the 1980s, who was a fully quantum person. And as far as he was concerned with saying, what happens if you have a higher spin symmetry in a two-dimensional quantum field theory? So that's the WN, you've got a spin N symmetry. How does that extend the Virasoro symmetry? And then it was observed by, oh, I've forgotten his name now. Anyway, it's observed that if you just did this classically, as n goes to infinity, you get this Poisson diffeomorphisms of the plane. So this little W infinity is the classical one, and that's just Poisson brackets of Hamiltonians on the plane. And so it's very easy to describe. You write your plane with two coordinates, mu alpha dot, alpha dot equals 0 dot and 1 dot, and you have a sort of a standard, relatively trivial Poisson structure, and then you start expanding your Hamiltonians in polynomials. And so here is just a generic monomial indexed by P and N. The index is slightly non-standard, but it's just designed so that I make contact with what was on the previous slides. And so on the plane, if you just do the Poisson bracket between two Hamiltonians of this type, Pn, Qn, you just get this. And this is already pretty close to what Andy Strometer had found. And if you want to have the extra index, there are three indices because you somehow expand. I mean, in the celestial story, the P was the mode associated with the energy, and then the M and N were associated with Z and Z bar, I guess. And so you had to finally put in some function of the Z. And then if you just compute the Poisson brackets here, the Z is not involved in the Poisson bracket. It's a free variable. It's a free loop algebra. So the RS goes to R plus S without anything complicated. But the P's and Q's and M's and N's sort of talk to each other in the Poisson bracket. So that's a fairly easy computation, and that sort of was part of the LW1 plus infinity story. But I've set up a notation so that this will not have escaped people. That a lot of people, well, Roger Penrose used omega and pi's, but sadly, the mu and lambda has become more familiar as coordinates on Twistor spaces. Yeah. No, this just depends on another loop variable. So a loop group, you just adjoin an extra variable, and you've got e to the minus IR theta there. Yeah. Well, the HPM's a polynomial. It's a monomial here. And this is now a function of three variables. This is a function of mu naught dot, mu 1 dot, and Z. Yeah, and so what's going to happen is that these are just very naturally functions on Twistor space. So if you set up your normal coordinates on Twistor space as a pair of spinners, so if these were omega and pi, the mu would be omega and the lambda would be pi. It's just Wisson went back to some old. Well, we're actually secretly working on dual Twistor space because we want to work with self-dual fields. Well, anyway, I shouldn't even say things like that because most people don't care. So you can think of these things as coordinates on Twistor space. And what we've done is we've written down a bunch of functions on Twistor space subject to a Poisson bracket, which is only really looking at the mu coordinates. So this is a well-known structure. So this Poisson bracket comes out of what's known as the infinity twistor. You might have, in twistor coordinates, you might have written this as something like I AB, d by dWA, d by of F, and dWB of G. And this is the structure that you introduce on Twistor space to break conformal invariance. Twistor correspondence is usually conformally invariant, and you break it. And this is non-degenerate up the fibers of the fibration over the Riemann sphere with homogeneous coordinates lambda. And this Z coordinate that's playing a role is thus the stereographic coordinates on the Riemann sphere. So, and this fits rather nicely into Roger Penrose's nonlinear graviton construction from how many years ago, nearly 50. And also, of course, into Ted Newman's theorem. So Roger's, in this language, then, there's one-to-one correspondence between self-dual, Ricci flat, holomorphic metrics on regions in we're thinking of them as holomorphic metrics in the complex. One can impose reality structures if one desires. Anyway, so you're thinking of these complex Ricci flat self-dual metrics. I missed out the word self-dual. Okay, sorry. Self-dual metrics on regions in C4 and deformations of Twistor space, preserving the fibration and the Poisson structure on the fibers. So in some sense, the first way in Twistor space that we're going to understand these symmetries, these LW1 plus infinity or Ham C2 loop group of Ham C2 symmetries, is simply as the local diffeomorphisms of Twistor space that preserve the nonlinear graviton structures, this Poisson bracket and this fibration over the Riemann sphere. So that's the first way in which we understand these celestial symmetries. Yeah. So, I mean, the deformations, the deformations, of course, preserve this Poisson structure and this projection. I'm not sure what you meant by Casimir's here. Right. I mean, these, because of course the Hamiltonians themselves, yeah, but these are invariant structures. So and it characterizes the group that they're the group that preserves that. Although we're making some choice here because we're allowing them to be singular at lambda naught equals 0 and lambda 1 equals 0. So there is some, but we regard that as a as a not very important gauge fixing. Okay, so the first way in which we're going to understand the symmetry is as a local diffeomorphism symmetry of the Twistor space that preserves the structures of a nonlinear graviton. But then there's an alternative way of thinking about it, because and this also appears in 1976 in Roger's paper. So what do you mean by deformation of a Twistor space? Well, the way in which he presented it in that paper was to say that you take your flat Twistor space, CP3, fibered over the Riemann sphere. So you take out a Linus infinity, so it fibers over the Riemann sphere. You choose two open sets, U and U tilde, and one of them could be lambda naught not equal to 0. The other one could be lambda 1 not equal to 0. And then you sort of shift the patching functions on the overlaps. And the fact that you the fact that you want to preserve the fibration means that these have to be vertical vector fields that you're using to shift the patching functions. And if you and if you want to preserve the Poisson structure, it has to be Hamiltonian. So so this patching function here has to be Poisson. And so so in some sense, what we're seeing here then is that if you take a loop in the overlap, then the space of deformations is the or the space of self-dual metrics then, according to Roger's theorem, is the loop group of these Poisson diffeomorphisms. So this patching function, the lambdas, of course, are the same going from one side to the other, but the mu's change to mu tilde, and it has to preserve the Poisson structure. And so in the way that Roger said it in this paper was to say that you needed to have a generating function to patch the two sides together. And he wrote a nice generating function down in this form. And infinitesimally, of course, such a thing gives rise to a Hamiltonian. And such a Hamiltonian, then, we could expand in these modes here. And so what we see then is we have this dual interpretation. On the one hand, these Hamiltonians here are deforming the complex structure. These correspond to gravitons, according to Roger's theorem. But on the other hand, they are local diffeomorphism symmetries. And okay, so and sort of nicely, if H doesn't have any poles, then it corresponds to, well, it doesn't actually quite give you the whole Poincare group. It only gives you the self-dual rotations. But anyway, so yeah.
Possible to see why this six.
Sorry, you were talking about self-dual metrics. So we're vacuum, but also this is like a characteristic description as well. So if you're on a Cauchy surface, you might have two functions of three variables, but if it's on a characteristic surface, you would expect that to halve. Yes, in that sense, because you only have the one Hamiltonian to give you the, yeah. Okay, so what we see is this twofold way of thinking about these things. On the one hand, they're symmetries. On the other hand, they're actually sort of representations of gravitons too. Well, we're being very simple here because the yeah, obviously, I know you had two, but you could have got away with one, but it's just it would have made your life more complicated in other ways, maybe, in your construction. And it's because the Riemann sphere can be covered in two patches. So you could have as many as you like, of course, but you could, in principle, always reduce it to just one patching function for a local solution in space-time. If you want to be global, then you might have other issues. Okay, so just to give a brief description as to how Roger's construction gives rise to a vacuum space-time, self-dual vacuum space-time. Well, this slide is really not so much to explain that theorem to you in full detail, but more to introduce a different way of presenting it. And so the way Roger did it was that he said that if you go back to this to Twistor space, I mean, I haven't really introduced the Twistor correspondence, but the way in which you represent points of space-time in Twistor space is as complex projective lines in CP3. And then the claim is that if you deform Twistor space, those degree 1 curves survive in a full 4-dimensional family. And so here we can see that I've got a picture here of this deformed Twistor space, and you still have this 4-dimensional family of these lines, and they you reconstruct a conformal structure by saying that the 2 points in space-time are null connected, but if the corresponding lines in Twistor space intersect in a point. Now, the point of this slide, though, is to introduce a different way of thinking about these constructions, and this will have two different roles, and that's as a Dolbeault construction. So in the Dolbeault construction, you don't worry about choosing patches and coverings. Instead, what you do is you deform the complex structure by deforming the d bar operator. And one way you can do that is you can introduce a 0-1 form on Twistor space. So just on the flat Twistor space now. Sorry, I mean, I've presented it as the curved one. And it has homogeneity degree 2. And the condition that the d bar operator preserves the Poisson bracket is the condition that that condition for holomorphy is deformed by adding on a Poisson bracket. So I haven't said this really in the best order. So these curves satisfy a differential equation. So these W's are going to be global coordinates in Twistor space, but now that they can depend on, if you fix a space-time point, they depend on Z and Z bar according to this relation. So to say this a bit more, sorry, actually, I think I've kind of done this a little bit in the wrong order, because I think I said it better on this slide here. Did I? No, okay. Well, I'll carry on in this order. It's slightly uncomfortable. What I want to do now is to sort of explain how you can do this from null infinity. So this was a story that was developed by George Sparling back in the 70s, I think. And then sort of there's a nice paper by Paul Todd and Mike Eastwood, which explains how George did it. So anyway, so just to set up the framework, if you have scry plus and minus, so again we have scry. It has a Bondi U parameter up the generators. It has Z and Z bar coordinates on the Riemann sphere, and then we will relate the lambda coordinates on Twistor space, the Riemann sphere one, to the Riemann sphere coordinate on scry, the space of generators of scry. So this is just going to be the same coordinate, but the rest of it will be a bit more subtle, as we'll see. Now, the data for the space-time is going to be given in terms of this asymptotic shear. This contains a self-dual gravitational data at scry. And it's really the leading term in the metric. Capital R is meant to be 1 over little r, the standard radius, and so this vanishes on scry. So this is a leading contribution. Okay, so then we can parameterize Twistor space in terms of scry. So the way that we do it is to say that the Twistor space is going to fiber over null infinity if you allow. So we're going to allow the U coordinates to become complex, but the Z and Z bar will remain as they are, just Riemann sphere coordinates. And then we have a fibration of Twistor space over scry given by these formulae. So the lambda and mu, lambda just gives us Z, but U now is given by this formula here. Basically the contraction of mu with lambda bar, but I've normalized it. And then the H that I told you before, which is what deforms the complex structure on Twistor space, is essentially the integral of the shear up the generators of scry. So you may be more comfortable for me to write that as that, you know, relation just a shear is equal to d by d u of this H of u lambda lambda bar. So the or Z bar maybe. So you can write down the complex structure on scry on the Twistor space at scry completely explicitly in terms of the shear if you allow yourself to do an integration. And so the D bar operator on the Twistor space is deformed by this kind of 0-1 form Hamiltonian H in terms of this formula. And then the Penrose-Nonlinear graviton construction can be understood as before by looking for the holomorphic curves with respect to this. And that actually, George Sparling and Eastwood and Todd and so on showed was equivalent to Ted Newman's original good cut equation at scry. Okay, so that's how this is the first step to take us out from the Twistor space description to null infinity. But what I've got to do now is I've got to actually, if I want to do some Noether arguments, I've got to write down an action principle. And then I've got to say that, that symmetries give rise to symmetries of the action, and you go through, you crank the Noether handle. So how are we going to do that? And so the reason I went to this Dolbo approach was because it gives you an off-shell framework, and you can therefore write down an action, and you can do Noether arguments. So now off-shell, the gravitational data is given by some 0-1 form on Twistor space of homogeneity degree 2 in the Twistor variables, and I realize my W's have mutated into Z's again. You see, I've become completely. I just never know whether I'm working on Twistor space or dual Twistor space. I'm so sorry. Okay, so I found plenty of these errors before yesterday when I was going through the slides, and I see some more here now. Well, everyone post-Witten worked on dual Twistor space. It's because you want to have a self-dual space-time, you know. Otherwise, you've got to work on an anti-self-dual space-time. And if you want to work with Zs. And then you can use your own and pi. So well, I'm sure that's right. Well, anyway, so there's a few of us diehards who just don't know where we are now, whether we're working on Twistor space, dual Twistor space, or anyway. Sorry. So that Z should have been a W, and my apologies. So this is these are both 0-1 forms. What H is going to correspond to the self-dual part of the data, and as before, on shell it can be given by the asymptotic shear, as I showed you on the previous slide. But if you're off shell, this could be any old 0-1 form on Twistor space of the appropriate weight. The G will actually again be a 0-1 form with weight -6, and off shell it could be any old thing, although on shell, if it's holomorphic, etc., will satisfy some D bar equation. And so the D bar equation then, to guarantee compatibility with the Poisson bracket, we're going to deform the D bar operator by just saying that we have the standard flat background on Twistor space plus the Poisson bracket of H with F. And then that will guarantee that this Poisson bracket remains holomorphic. And the integrability of this almost complex structure is going to give rise to this self-dual field equation, which, and I've got 10 minutes left. This self-dual field equation, d bar naught H plus half the Poisson bracket with itself is 0. And then this G, which should have been lowercase, is also holomorphic, d bar closed. And so in linear theory, of course, you just say that H and G were d bar closed, but you get this nonlinear term on the background. And so you can write down a kind of Chern-Simons-like, well, BF-like formula for these equations very simply. So G is essentially a Lagrange multiplier for the H equation. And then if you vary H, you'll get this equation on and that capital G should be lowercase. Okay, I apologize for the number of, I corrected so many errors yesterday and I've still got plenty more here. Okay. Anyway, so this is the self-dual Twistor action as a holomorphic Poisson Chern-Simons action. You think of this as, it's only really Chern-Simons like if you extend it to supergravity. At this point, it's what people would call BF, or Lagrange multiplier action. But it encodes both the self-dual and the anti-self-dual data. And so what about the symmetries? How are they realized? Well, these are now just straightforward gauge symmetries in this language. So you have a gauge symmetry. You see, really, we're thinking of this H and the G as describing elements of, in linear theory, cohomology groups. So you can add on D bar exact terms. And so a D bar exact term might look like something like this. So G is, you add on D bar sub H of chi, where chi is some scalar of weight -6. And to H, you add on D bar sub H of psi, where that has weight 2. But this is actually really generating a Poisson, a smooth local Poisson diffeomorphism. So it drags G around as well, like that. And so you can go through the Noether arguments. You can write down the symplectic form. people have elevated these ideas to a name of covariant phase-space formalism. And but I guess they go back a century or two, and then you you find the Hamiltonians that generate the Hamiltonians. So this is now so the action was on the full six-dimensional Twistor space. This is now thought of as a kind of like a Cauchy surface in the Twistor space. It's a 5-manifold, and so you get a full Hamiltonian charge integral that's given by this kind of expression that generates these gauge transformations. And they do the honest thing. They represent, if you compute the phase space Poisson bracket with this symplectic form on these charges, you'll get the Poisson bracket on the diffeomorphism generators and the obvious sort of action you might have expected on the gauge transformations for G. So that's all quite nice. And then according to Noether's theorem, that if these are gauge transformations, so their local Hamiltonian density vanishes, and that means that their boundary term comes down to the actual value of the Hamiltonian is generated by a boundary term as infinity. So we go to the boundary of this 5-dimensional sort of, maybe think of it as a Cauchy surface in Twistor space. So it's a 4-dimensional space, and we're going to think of this 4-dimensional space here on the. So first of all, this is the charge integral that you get. These are the boundary charges, and we're going to think of that 4-dimensional boundary as being sort of like a 2-surface at infinity at scry, or maybe even I0. And then but it's a 4-manifold because each point of scry corresponds to a sphere in Twistor space. But as above, we expect to get the correct charge algebra. And really, the business part of this is going to be the Xi. The Xi is the thing that's coefficient of G generates the gauge transformations in H, and they generate the Poisson diffeomorphisms. Now, if you want this to be an honest symmetry, it has to not vary G and H as infinity. It means they had to be holomorphic at infinity. If they were global, then they would be quadratic because they have homogeneity degree 2, and that gives rise to this kind of Poincare group. And you can check that that all works. But for this local, these more general diffeomorphisms, we can take them to be these LW1 plus infinity generators that we had before in these holomorphic coordinates near this surface at infinity. And I'm very short of time now. Yes, okay. So okay, so you've now got to do the calculation. Okay, so this gives you an answer on Twistor space, but even in this room, I don't know how many people truly live on Twistor space. I mean, yeah, not even sure that. Yeah, sorry. I even look at some of my best friends. I'm not sure they really live on Twistor space. No, I don't know. You know, I mean, but I was sort of happy. I was happy with this answer. I thought I was done when I got to this point. But anyway, for most people, you're not done until you can actually relate it to something they can deal with in space-time. And what about those Friedel, Pensetti, Riccariu charges? You know, how did they come about? How do you see those coming out of a simple formula like this? I mean, this is just one term. I've got to integrate it against G. That's it. What's to say? And so, okay, I've got to actually see how to fit the Penrose transform into that formula. This is still actually quite a complicated 4-dimensional integral here. And as I said, we're really looking at that first term, psi G. It's a 4-dimensional integral. And so to get down to a 2-surface, which I can take to be at scry, say, this S is going to be a 2-surface at scry, I've got to integrate out that Riemann sphere. Yeah. Yeah. One that ends at scry. I mean, so what I'm doing is I'm really secretly taking a Cauchy surface in space-time, and then each of those points on that Cauchy surface corresponds to a 2-sphere in Twistor space, and that gives rise, so it's 3-dimensional Cauchy surface gives rise to a 5-surface in Twistor space. And then the boundary of that is a 2-surface in space-time times a Riemann sphere in Twistor space. No, I haven't really kind of been that specific. And in many ways, this two surface is, I'm going to want to really think of it as being near I0. So I can think of these fields H and so on as being kind of going to zero there. Okay, so I've got to get a bit more kind of grubby with things to write down a formula. So I said that Twistor space phi-bit over scry, so long as I let this variable u become complex. And another way to say that then is that I could sort of just add another coordinate to Twistor space. So Z, we've already said, was the Riemann sphere coordinates and comparable to the lambda coordinates. But then the mu, then part of it is given by the u coordinates on scry, but there's another coordinate q, which is going to go up the, thought of as a Riemann sphere coordinate that's going to be this extra Riemann sphere at scry. So this q, each point of scry corresponds to a Riemann sphere in Twistor space. Q is going to be a coordinate on that Riemann sphere. And then my claim is, you see, that I can actually write down an integral formula for the anti-self-dual asymptotic Weil spinner. So these psi naught n's, well, I'm going to call them q's, but certainly for n equals 0, 2, and 3, these are just the asymptotic anti-self-dual Weil spinner control components, and they're given in terms of the 0, 1 form that I call G. And here's a formula that was written down by, at least I think Paul proved it, and Branson sort of suggested this. I don't know, is that right? Back in a long time ago. This is, I think, a Twist newsletter from 1979. Yeah. So there are not too many people who have a memory of Twist newsletters from sort of. Anyway, sorry. So the cute thing is going to be that if you let this S index go on forever, positively, then these Qs fulfill the equation that Pransesi, Vaccariou, sort of Friedel, FPR wrote down. So these are the asymptotic Bianchi identities for S between -1 and 3, but then but it carries on and gives their equations. And so if you're seeking to do this integral over a surface of constant u, this tells you how to integrate out the q's. So if you can take, so what I was doing here then was I was writing down the psi. So I can expand this psi in powers of q, and then the rest of it will give rise to a formula that you can understand in terms of these curly q's, which are essentially a continuation of the Weil spinor components at scry. But still, I mean, this doesn't quite explain the complexity of the formula I showed you before, and I'm out of time. So there you go. I mean, that's it. So what went wrong? Well, there's some gauge fixing we had to do. We had to correct the gauge. It pushed us out of this scry gauge, and it's all explained there. And then you get this, and that's how it all comes out. So, but yeah, maybe I should actually stop because well, I mean, just to say, you see, the H that we represented in terms of the shear had no Q dependence. So this was, so the gauge fixing was that H should have no Q dependence. But this then imposes a condition on psi. And so if you start off with the general psi, you've got to correct it. You've got to add on some extra term to push you back into this gauge. And that's the source of all of these sort of horrendous extra terms you get here in these formulae, and it just goes on, and they get more and more complicated. So if you live in Twistor space, your life is simple. If you want to live on scry, I'm sorry to say that it's very messy. And well, I mean, I guess yeah, that's actually yeah, you're asking difficult questions. Okay. Oh, no, oh, sorry, the other holistic charges. Oh, no, sorry, you can write them down. They just don't do much. They're not very interesting. Sorry, no, those charges you can write down and yeah. Okay, so the takeaway points then is the Penrose nonlinear graviton construction actually identifies the local holomorphic diffeomorphisms of Twistor space that preserve the Poisson bracket with self-dual gravitons. And so hence this idea that the in celestial holography, that the operator that corresponds to modes of the graviton should also be understood as some symmetry algebra. And but the most efficient way to understand the action of these is the via this Twistor action for the self-dual sector. And back here, I forgot to really mention that this just cranking up the power of Q here in this formula was really the main idea in my paper with Matt Schick from 2000 or whatever it was, the hypercalar hierarchies. Yeah, you know, that just saying, okay, what happens if you just allow any arbitrary power there. So this story is a story about the recursion operator and the hierarchies for the self-dual sector, but may be represented in terms of data at null infinity. And anyway, but it gives us systematics. So these guys didn't have systematics. They were essentially guessing. Bootstrapping is the term that people often use. Therefore, they didn't really have an argument from first principles. Anyway, so celestial symmetry is a symmetry of the self-dual sector. So they're big questions. Sorry, I thought the difficult question that Asa was asking was what about the anti-self-dual counterparts, and can you understand those on Twistor space as well, and so on. And they act locally on Twistor space, but they're not local on Scry. They can be made to act locally on the cotangent on the Scry, but not on Scry itself. And anyway, there are lots of good things we could do with it, but I better stop. And thank you very much. Yeah. There you go. And then there's this nice paper by Roland and friends. Yeah, Simon not here, but anyway. Where we did that, and we got a different algebra, which sorry, I forgot what we called it. Yeah. Anyway, we had another name for it, but it's but it was the same thing anyway. But with a non-degenerate Poisson structure. Yeah.
Just something that for a while is in L Hamilton squared. So some of the Hamiltonians, a very small number, are symmetry classmates.
Yeah.
And some of them are actually gravitons.
Mm-hmm.
And some of them seem to come from restriction from either lambda naught is non-zero or lambda 1 is non-zero. So
absolutely. Yeah.
Why should I?
I'm not sure that I have a good theory of these things. So when I was playing with these ideas back in the 80s and 90s with Nick Woodhouse and then with Maciek, we were trying to understand where these infinite transformation groups were coming from for integrable systems, and the answer was obviously they were coming from these very simple. For Yang-Mills, it was just once you've chosen the trivialization of your bundle, then it's just the group of maps from the overlap on Twistor space to the group. Very simple group. But as you say, some of those are simply gauge transformations. If they extend over one side or the other, they are just gauge transformations. And so their status is a little bit suspect. But on the other hand, you wouldn't, if you tried to quotient by them, you would no longer get a group. So in a sense, what happened was that if you reduce by two variables, you would find that you had canonical ways to fix those gauges. and then you could get an honest group. So the Grouch group is pretty honorable, although it still has that ambiguity by constants. So what was left in these two-dimensional systems was still a very analogous ambiguity, but because it was constants, people wouldn't worry about them so much. But I think there needs to be a theory of what you mean by a local symmetry like this, as opposed to, yeah. And also, I don't like the fact that at some point I found myself saying we choose a gauge in which h is 0 near lambda naught equals 0 and lambda 1 equals 0. Sure, you can do that, but you don't want to have to do that. So there must be a way of saying it that's more geometric, and but you end up tying yourself in knots if you try to do it too much. Sorry, this is Claude. So the heaven on earth construction was to say, so basically, so George explained how to build a deformed Twistor space from null infinity. Claude did something very similar, starting off from a space-like hypersurface. And but then you can ask, that just gives rise to a general conformally self-dual manifold. And if you want an Einstein manifold, then the natural thing to do is to think of that sort of space-like hypersurface as being the conformal infinity of a Poincare-Einstein manifold. And so if you have cosmological constant, then it's very natural to think, especially if you're a Euclidean signature-minded person like Claude, to think of an infinity that's sort of maybe like S3, and then use that to build your Twistor space. So you start off with an Earth. I suppose that's heaven on Earth, but then you still build a self-dual space-time, and that Earth ends up being at infinity in heaven.
When you mentioned this early work from Newman or the woodcut, is there anyone do something similar for this generalization that we found in light contact? This null surface formulation where he reconstructs the manifold not from sky but from a null surface, and I believe this is called light contact.
Sorry, I sort of remember. So there was a formulation where you somehow sort of just try to construct locally. So the Bondi coordinates on a region in space-time, essentially, I'm sure one could do that, but one does lose some of the structure. So the canonical nature of some of those things becomes. But you could use formally in coordinates that look very similar. And me too, actually. Yeah. So I quite liked it. I thought it was quite nice. Yeah. So you have to basically what you do is you say I'm going to solve the Eichenal equation for all null directions, not all complex null directions, but maybe you do want to include a sphere in the space of all null directions. But the real problem with that is the ability to actually identify a canonical complex structure on this sphere. That was the problem, and it's sort of a bit unnatural. But I quite liked it all the same. I can give you a reference to a paper where I did some of that, and I was very pleased with some of the equations you get in the linear theory, but they get horrible in non-linear case.
But you get rid of the self-duality.
There is no self-duality constraint. That's right, and there may be some mileage in this. I don't know, but I certainly gave up. Yeah. We did, yes, yeah, and I'm sure we didn't know. Well, maybe we should have a Newman tribute volume where we can do something that he'd hate, string theory in heaven or something. Thank you.